Hello everyone. This is my presentation for our final report, and it has a topic of grounding grid design and simulation using ETAP. This project is submitted by Arpit Patel, myself, and Asad Mahmood. He is my colleague, and this project has been submitted to Mr. Dr. Mohsin Jamil. So let's start the presentation. Here is the table of contents in which we are introducing our project. It has a methodology that we have followed for building this project using ETAP, and then we have our grounding grid model, which we will show in the upcoming slide. Then we have the single line diagram, which we all need to perform the operation of construction of grounding grid designing. Then there is our first simulation result. Actually, this is the result and that we performed. After that, we optimized the grid parameters based on the results of the first simulation. And then finally, we did our final simulation results. So that is all we are going to present in this presentation. So, and we will comparing both the grid design before and after optimizing the results. So in the introduction here, we have like the grounding grid in our project is designed as per IEEE 80 standard in ETAP. The IEEE 80 standard is developed by the Institute of Electrical and Electronics Engineers, IEEE, which offers the guidelines for grounding industrial and commercial power systems. It provides the recommendations for designing, installing, testing, and maintaining the grounding systems for ensuring the safety and reliability. Compliance with this standard helps mitigate risks associated with electrical faults and lightning strikes. So the grounding grid design involves consideration of multiple variables, including the mesh voltage and step voltage. Step voltage is the voltage difference between the 2 points on the ground surface, typically caused by a current flowing through the earth fault during the fault condition. So that's the step voltage. Touch voltage is the voltage experienced by a person or an individual which touches an object within a potential difference due to the fault currents, posing a risk of electric shock. Various shapes of grounding grid exist, such as square, rectangular, T-shape, and L-shape, with each possibly incorporating grounding rods in it. Comparative studies referencing IEEE standards and research sources help us to evaluate different grid shapes effectiveness as per the application of use. So basically, like for a particular application, we can use a square shape grid also, for rectangular shapes grid also. So it depends on the type of application that you are using. For this project, we are using the rectangular grid. So along with that, this whole project is made in a software called ETAP, and there is one another software called CYM Grid, aids in analyzing grounding grid design and their impacts on the conductor selection. So the methodology here is due to the various variables involved. The design of substation grounding grid system is quite complicated. They are allowable and estimated grounding resistance, uh, GPR, mesh voltage, step voltage calculations that we need to do. And here is the formula for calculating the grid grounding resistance in its uniform soil using the given below formula. So here is the formula which we have taken from the one of the reference materials, and the references are quoted at the end of this presentation. So how we used to calculate for the step voltage and mesh voltage, it is shown here in the formulas given below. As you can see, the parameters that are involved are rho, which is the crush rock resistivity, T, which is the fault duration second, Ig is the maximum fault current, and Ls is the total length of the buried conductor, which is in meter. Lm is the effective length of the grounding grid, and Yeah, here are some of the spacing factors like Km, Ks, and Ki, which are used for the mesh voltage calculation, and spacing factor for step voltage and correction factor for the grid geometry. So as we are making this presentation, as we are making this project, it aligns with the standard reference of IEEE 80. It has been designed in such a way that IEEE 80 states that the grounding grid should be used for the safe operations. As we all know, it is a very useful thing in the substation grounding, and it has a compliance which ensures the mesh voltage remains below the tolerable touch voltage, and the calculated step voltage should be lower than the tolerable limits. Of course, these conditions needs to be met so that a safe operation can be followed in any of the substation, right? To protect the personal individual or a person working over there. Mesh voltage represents the maximum touch voltage. Okay, so here is the grounding grid model. Like this is the single line diagram that we have generated in the ETAP. And as you can see here, like there is a bus 1 of 11 kV. Then there is a bus 2 which has a transformer of 2 MVA. Then there is one lump load of 0.3 MVA. Then along with that, on the bus 1 we have our motor 1, which has a horsepower of 800, and lump 4, which is 0.4 MVA. So this is how we made in our ETAP. This is the single line diagram. Along with that, there is a one grid, as you can see in the green color picture. That's our grounding grid. Now the specifications of the circuit components, as you can see, like we have used the synchronous generator. So the ratings are as below, which has a power capacity of 10 megawatts, voltage of 11 kV, power factor 85%, and impedance, that is the default value that's given in the ETAP. So as you can see, the parameters of synchronous generators that we have selected for the uh, application. Then there is induction motor, that as you saw in the single line diagram. So the induction motor ratings are as given below, which it has a power rating of 800 horsepower, which is equivalent to 596.56 kilowatt, voltage of 11 kV as usual, and speed is 1800 rpm. So these are the nameplate parameters of an induction machine editor that we have selected. And here are the specifications of the lump load editor, as you can see in the slide, about their ratings and how they are placed on the single line diagram. So here is the grounding grid design in the rectangular shape with the length of 50 meter by length of 50 meter and breadth of 20 meter, with the conductors placed on the x-axis are 3 in numbers, and in the y-axis are 2 in numbers. The conductor depth is selected as 0.5 meter. Area of the conductors is 120 square mm. Type of material is copper clad steel wire. Also the material constant like resistivity, alpha factor, K factor, fusing temperature, resistivity, thermal capacity are all the factors which will change as per the type of material. So this is all these factors are dependent on the type of material. Along with this copper clad steel wire, there are other materials as well, like aluminum and all other type of material as that is available in the ETAP software. So based on the application, you can select from it. Here for this project, we have selected the copper clad steel wire.
Thank you, Arpit, for your presentation and giving me the opportunity to speak. Thank you, Arpit, for your presentation. Now I will continue onward. So, in this slide, we will discuss the grid study case editor. So here we have following parameters for the grid case studies. So fault duration of the system is 0.5 second. Short circuit study at 5.171 ampere. So we have been using here the method IEEE 80 dash 2000 slash 2013. In this slide, we will be discussing first simulation result. So the short circuit test analysis on the grid we have designed, the following result came. Here the calculated voltage exceed the tolerable voltage limits. So the same thing happened with the step voltage. So we have to make some changes in the grid we have designed. So we will see in the next slide what happened after that. In this slide, we are discussing optimizing the grid parameters. So ETAP software provide us the opportunity for optimization by increasing the conductors and rods quantities and size to get the desirable result. So we implemented suggestion which are given by the ETAP software. So we have make changes accordingly. So we have four conductors in y direction. So after the suggestion, we have make them uh, seven by adding three more conductor in y direction. So we have made changes in the design grid by the suggestion given from ETAP software. So we have increased the number of rods and the number of conductors in X and Y direction. So after that we will see what we have result now. Here we have the final simulation results. So we can see here the calculated voltages and tolerable voltages for touch and step voltages. So here we have the calculated voltages less than tolerable voltages, which will work for our design. It will make our design perfect. So there are also no any indication or alarm which we have to clear. So it's mean our design is perfect as per the standards and specification given. In this slide we can see the optimizing result which have done by the ETAP software. Before optimization we have only two conductors in y direction. So after ETAP's software suggestion, we have added five more conductor in y direction. So this was our presentation for the designing of grounding grid by using ETAP software. So thank you so much.